The mean value theorem. First, let's start with Rolle's theorem. Let f be a function that satisfies the following three hypotheses. F is continuous on the closed interval from a to b. F is differentiable on the open interval from a to b. And let f of a be equal to f of b. If these are true, then there is a number c in the open interval from a to b such that f prime of c is equal to 0. Let's take a look at these graphs to help us understand Rolle's theorem. So first of all, let's start with the third thing. F of a is equal to f of b means that these two values are the same. F is continuous on the closed interval means that you can graph the function from this point to the other point without lifting your pen off the paper. And the third thing, f is differentiable on the open interval means that your function is smooth, no sharp edges, and not infinitely steep. If those three hypotheses are true, then there will always be at least one number c strictly in between a and b, such that f prime of c is equal to 0. In other words, we have a flat tangent line. Now, the next graph shows essentially the same thing. We have f of a is equal to f of b. We can see that it's continuous, it's smooth, but this time you can see there are actually two values at which the derivative is 0. And the third graph is much like the first graph. So these graphs give us an idea that this is intuitively true. Let's do an example. Here we want to verify that the function satisfies the three hypotheses of Rolle's theorem on the given interval. Then we want to find all numbers c that satisfy the conclusion of Rolle's theorem. So first, let's just note that f of x is a polynomial function. So f of x is continuous on the interval from -2 to +2. Yes, this is true because polynomial functions are continuous everywhere. Secondly, f of x is differentiable on the open interval. Yes, this is also true because polynomials are differentiable everywhere. And the third thing we need to show is that f of a is equal to f of b, which in this case means f of -2 is equal to f of +2. So let's go ahead and plug those in to verify. F of -2 is going to be -2 to the third power minus 2 times -2 squared minus 4 times -2 plus 2. And this is -8 minus 8 plus 8 plus 2, which is equal to -6. F of 2 is equal to 2 to the third power minus 2 times 2 squared minus 4 times 2 plus 2. And this is 8 minus 8 minus 8 plus 2, which is -6. So we now know that the three hypotheses of Rolle's theorem are true. So now we want to find all values that satisfy Rolle's theorem. The conclusion of Rolle's theorem is that f prime of c must be equal to 0 for some value of c that is strictly in between, in this case, -2 and +2. So let's take the derivative. F prime of x is 3x squared minus 4x minus 4. Therefore, f prime of c is going to be 3c squared minus 4 times c minus 4. And if we set f prime of c equal to 0, we can solve this equation for c. Now, it's possible that you might be able to factor, but if you're not able to factor, you can always use the quadratic formula. I think this factors, so let's give it a try. So we have 3c times c, that will give us 3c squared. Let's try 2 times 2, and let's put a negative here and a positive here. And if you double check this, you will see that you get 3c squared minus 6c plus 2c minus 4. And that does equal this quadratic. So now we'll set each of these equal to 0. And here we get c equals negative 2/3. And here we get c equals 2. So we have two possible solutions for c. Now, let's make sure we realize that c has to be strictly in between negative 2 and positive 2. So what that means is that c cannot actually be equal to 2. It has to be in between. So negative 2/3 is a value in between negative 2 and positive 2, and that is the value that satisfies Rolle's theorem in this case. Rolle's theorem is actually a special case of a theorem called the mean value theorem. The mean value theorem states, let f be a function that satisfies the following hypotheses. F is continuous on the closed interval. F is differentiable on the open interval. If this is true, then there is a number c strictly in between a and b, such that f prime of c is equal to f of b minus f of a divided by b minus a. Or, equivalently, you can write that as f of b minus f of a must be equal to f prime of c times b minus a. The first thing I want to point out is that there are only two hypotheses here. Remember, Rolle's theorem had a third hypothesis that said f of a is equal to f of b. Now, if that's true, then that means that f of b minus f of a would be equal to 0. And if that's true, then that means that this would be 0. And this would become f prime of c is equal to 0. So with Rolle's theorem, you have the one extra hypothesis, and that leads to a little bit simpler of a conclusion. All right, now let's focus on the mean value theorem. The mean value theorem does not state that f of a has to equal f of b. And so what is the meaning of the mean value theorem intuitively? Well, let's take a look at a graph. Suppose we have a function that is continuous and differentiable. And let's suppose that f of b minus f of a divided by b minus a exists. And I want you to notice that this is nothing more than the slope of the secant line. So you should actually recognize this from our earlier discussions, that this is the slope of the secant line through the point at x equals a and x equals b. F prime of c is the slope of the tangent line at x equals c. So the mean value theorem says that there will always be a number c somewhere in between a and b, such that the slope of the tangent line at c is equal to the slope of the secant line through these 2 points. In other words, there is always going to be a point where the slope of the tangent line and the slope of the secant line are equal, which means the lines are parallel. Another way to interpret this is that the slope of the secant line is the average rate of change and the slope of the tangent line is the instantaneous rate of change. And so it basically just says that the instantaneous rate of change must be equal to the average rate of change somewhere in the interval. Now, there could be more than one value of c, so here's another graph to consider. Here we have a continuous function, and it's also differentiable. It's nice and smooth. We can see the slope of the secant line is here. Notice there is a value c1 at which the tangent line is parallel to the secant line, and also there is a value c2 at which the slope of the tangent line and the slope of the secant line are the same. So there could be more than one value, but the mean value theorem only guarantees that you will be able to find at least one. Let's take a look at an example. So here it says to verify that the function satisfies the hypotheses of the mean value theorem on the given interval. Then find all numbers c that satisfy the conclusion of the mean value theorem. So again, this is a pretty straightforward exercise. F of x is continuous on the interval from -2 to 2. Yes, that's true because f of x is a polynomial, and polynomials are continuous everywhere. And f of x is differentiable on the same interval. Yes, this is also true because polynomials are differentiable everywhere. Now, we don't have to find f of a and f of b to prove that they are equal to each other. So there's only two hypotheses that need to be satisfied for the mean value theorem, and we can see that they are satisfied. So now let's find the value that satisfies the mean value theorem. So the mean value theorem says there exists a number c such that c is first of all between a and b, and f prime of c is equal to f of b minus f of a divided by b minus a. Now, to find the value c, we will need to compute f of a, f of b, and we will also need f prime of x. So let's go ahead and compute these things. F of a is going to be f of -2, since a is -2, and that is -2 to the third power minus 3 times -2 plus 2, and this is equal to 0. F of b is going to be f of +2, and this is 2 to the third power minus 3 times 2 plus 2, and this is 8 minus 6 plus 2, which is equal to 4. And f prime of x is 3x squared minus 3, which means that f prime of c would simply be 3c squared minus 3. Now we're going to use the mean value theorem, which says f prime of c must be equal to f of b minus f of a divided by b minus a. F prime of c is 3c squared minus 3. F of b is 4 minus f of a is 0. And we're dividing by b minus a, which is 2 minus -2. And so this is 3c squared minus 3 is equal to 4 divided by 4, which of course is 1. And then if I add 3 to both sides, I get 3c squared is equal to 4. Dividing by 3 gives us c squared equals 4/3. And finally, c should be plus or minus the square root of 4/3. And if I simplify this, I get 2 divided by radical 3. And sometimes we'll want to rationalize the denominator like so. And in that case, we would get plus or minus 2 radical 3 divided by 3. And you could approximate these values to see that it's between -2 and 2. And these are approximately plus or minus 1.15. And both of those values are in between -2 and +2. So this is a case where we have two values that satisfy the mean value theorem. And for our final example, we want to find the number c that satisfies the conclusion of the mean value theorem on the given interval. And then we're going to graph the function, the secant line, and the tangent line to show graphically that it satisfies the mean value theorem. So once again, we need f of b and f of a, and we need f prime of x. So f of b is going to be f of 2, and in this case that is e to the -2. F of a is f of 0, which is e to the 0, which we actually can simplify and say that that's 1. And f prime of x, the derivative of e to the -x, is e to the -x times the derivative of -x, which is -1. And so we can write the derivative as negative e to the -x. So then f prime of c would simply be negative e to the -c. So now the mean value theorem says there must exist a number c such that f prime of c is equal to f of b minus f of a divided by b minus a. F prime of c is negative e to the -c. F of b is e to the -2 minus f of a is 1, and then divided by b minus a, which is 2 minus 0. Now, we need to solve for c here, and this is not trivial, and it actually is a lot harder when you have negative exponents. So I'm going to write my negative exponents as positive exponents. So let's remember that when you have something like x to the -n, this is the same as 1 over x to the positive n. So negative e to the -c can be rewritten as -1 divided by e to the c. E to the -2 is 1 over e squared, minus 1, and then divided by 2 minus 0 is 2. Now I'm going to multiply both sides by -1. That will cancel out the negative sign here, and we have 1 over e to the c is equal to, now on the other side, when you multiply by -1 to both of these, it's just going to reverse the subtraction. So we'll have 1 minus 1 over e squared divided by 2. Okay, so now to simplify this, I'm going to multiply the top and bottom here by e squared. And this will give us 1 over e to the c is equal to e squared minus 1 divided by 2e squared. So again, I'm just multiplying here, and canceling the denominator. And now if I take the reciprocal of this fraction, we get e to the c over 1. And I'm going to take the reciprocal of the other side, which is 2e squared over e squared minus 1. Okay, now the divided by 1 here we can get rid of. And how do you solve this for c? Well, you remember you need to take a natural log of both sides. And the natural log of e to the c is just c. And then we have the natural log of 2e squared over e squared minus 1. And let's go ahead and bring in the approximation for this. And we can see this approximation is about 0.839. And let's remind ourselves that that number is acceptable because the mean value theorem says your number has to be between, in this case, 0 and 2. And 0.839 is between those numbers. Now let's bring in a graph to show what this looks like. So you can see we have the function e to the negative x, that is this blue graph here, from x equals 0 to x equals 2. Then we have the secant line going through the endpoints of that graph. And here is the parallel tangent line. And you can see that the tangent line is parallel when x is equal to 0.839, which I'll remind you is the value that we found down here. So we can see that it works. The mean value theorem does indeed give us a value c somewhere in between a and b, such that the slope of the tangent line and the slope of the secant line are the same, meaning the lines are parallel. And that concludes this video lesson.